All right, gentlemen, good morning. This class is a production lathe class. We will be generating toolpath for this particular part that you see on screen. We will take a series of predefined tools, do facing, turning, grooving, threading, and some ID operations on this particular part. I'm sure all of you have seen it at some point. If you've been using Gibbs for any amount of time, you've probably seen this part as one of the exercises or in the manuals. What I'm going to do is simply go through the interface for a simple production lathe part. We're working with the assumption that no one has seen the system or used the system, so some of the terminology and some of the features that I show may be redundant to some of you. Some of you new time users might be able to pick up a few things here, and even the older users might pick up a few tricks or tips here and there. Initially, we start programming with a piece of geometry. This geometry was drawn in gibbscam based off of one of our blueprints. The manner in which you get the geometry into the system is really not that important. You can draw within the system, or you can import DXF, IGES information, or if you are working with the solids, you can import a solid into the lathe package and use one of the plugins to extract a profile for machining. Currently, gibbscam does not support the machining or turning of a solid model in production lathe. What I'm going to do is go through the interface and show you how to construct a series of tools and tool paths based on existing geometry. We won't spend time drawing the geometry. We're simply going to go ahead and use a file that I have imported in. We are working with the assumption that all of us can connect to geometry or pretty much know how to get geometry on screen. The document control dialog is one of the first things that is accessed when starting a file. The machine selection is done up here in the drop-down menu that has a series of different machine options. This is the MDD selection. MDD stands for Machine Definition Document. Whenever you see the term MDD, we are typically speaking about a machine type. In my drop-down menu, you're going to see a larger assortment than what you have in your application. This is simply because I have loaded different MDDs for different machine types. The machine selection for a simple production lathe is a horizontal lathe with a generic shank. Horizontal lathe, generic shank is a simple production setup. The generic shank designation allows you to select the shank size down in the bottom window. The shank size does not affect the toolpath or the machining in any way. What the shank size does is it shows us the actual tool holder when we activate the tool holder icon right up here in the taskbar. The material selection. If you have the cut data option purchased, you come in here and in the drop-down menu, select the material that you will be machining. We're going to say that this part is made from 6061 T6 aluminum. So we're going to set up the selection set appropriately. The family is aluminum alloys in the rot condition. The hardness of the material is in the higher temper range of 75 to 150. In the H scale, we can always do a conversion to different scales, hardness scales. And in the alloy window, if I scroll down a bit, I'll see that 6061 is part of my selection set. The alloys in this window are not selectable. They're simply there to visualize what materials conditions you have selected. The input units can be inch or millimeter. In this particular case, they are an inch. If we had a need to program in millimeters, the button for millimeters is that selected. It is not advised to change units in the middle of a part. If, in fact, you are working with a part that is defined in inch units, it is not a good idea to change to millimeters in the middle of the part. What this does is it alters the size of the units and converts from inch to millimeter. If you have to do a conversion within the program, it's best to do the conversion on one of the dialog windows and divide or multiply by 25.4 to get the conversion. The global settings for solids remains grayed out because, as I mentioned previously, we do not machine solids in production lathe. The open, new, save as, and save copy and close buttons are duplicated from the file menu. You'll see the same assortment on the file menu. They're simply localized here for convenience. In the bottom window, this is actually two windows. You can take them apart. In the bottom window is where we define our stock. Stock definition is based from the finished face of the part. The distance in the Z negative direction is towards the chuck. Z positive is typically material that's going to be left on the face for removal. And we have the option of programming radially or in diameter. The best approach in this case is to select the diameter setting and simply put in the values diametrically right off the blueprint. The X starting diameter is 3.5, assuming we're starting with 3.5 inch stock. And auto clearance is selected. Auto clearance is a very handy feature that allows the system to track where the material is and avoid it by a clearance amount. In other words, if we're taking multiple passes, each pass will be cleared 100 by 100 thousandths before retracting and repositioning for the subsequent cut. There are two options for clearance settings. Auto clearance, system controlled values based on this clearance setting, or if you uncheck auto clearance, you can use a user-defined clearance. In this case, I'm going to type in 3.5 and Z.1. This user-defined clearance sets a fixed set point for all moves to clear to. The difference is that auto clearance is more efficient because the system looks at the stock and the part and clears it automatically, avoiding any feeding in air or unnecessary motions. The tool change checkbox, when activated, gives us an absolute position based on part 0. Tool change position is handy when working with very short work that is barely protruding out of the chuck, and you don't want to travel all the way to home to index the turret. Tool change position is typically thought of as a G30 command on most production lathes. This is a secondary home or secondary tool change position. This can be set as an absolute value in diameter and in Z. We're going to leave this unchecked for now. The holder or the shank that's going to hold the insert is defined in this drop-down menu here. We've got 4 options: 1/2 inch shank, 3/4 inch shank, 1 inch shank. The 1.5 inch shank is usually for the larger machines. We're going to go with a pretty standard selection of a 1 inch shank. If, in fact, we were setting up a mill turn machine that had live tooling, we would select the mill holder class from this drop-down menu. In this particular case, we're doing turning only, so we have no need for a mill holder. So this has no bearing on what we're going to do with the part. Comments are program comments. Typically the name of the part or part number. Let's give it a part number of 1, 2, 3, 4. and call out the material as aluminum 6061 T6. Any information that you want to relay out to the machine control can be typed in as a program comment, and it will appear as a man readable. The comments here are at the header of the generated G code. All right, having set all these values, we can close the dialog window, and I'm going to open my view control palette and look at it in the isometric view. What we see here is the part geometry defined on an XZ coordinate system within the defined stock. The origin of the part, X is centerline, Z0 is the finished face of the part. What we need to do is keep our cuts within this boundary. I'm going to turn on the rendering option. Rendering is activated in this tile here, and we're going to take a look at the stock condition. The rendered image is based on the stock definition from the dialog window. We have options in how we view this stock image. In the taskbar, there is a show lathe stock cutaway. If this is activated, we will see a 3/4 view that will allow us to view any machining on the ID of the part. Another click on this tile gives us a half view of the stock, and this is nice if you're doing machining from a lower turret on a NTM situation and you want to change the view of the rendered stock and see it cut from the bottom. You can go to half view or full view, which is commonly used when doing mill turn applications or NTM, and you have milling or cross drilling on the OD of the part that needs to be viewed in this selection. Turn off rendering. Take a look at the stock. We have a feature where if we turn on rendering, we can superimpose the stock by going to the view menu and showing geometry. And we can superimpose the stock onto the rendered image and see if we've overcut or stayed within the boundaries of our geometry. If I activate the flash CPR, we'll see all the machining take place, the threading, and the part finishes up with, I believe, 12 operations. EOP stands for end of program. What I'm going to do is keep the tools, and I'm going to delete all the operations and walk through performing the machining on this piece of geometry. To select all the operations for deletion, I click on the top first operation, hold the shift key, click on the last operation, and all of the operations in between those two tiles select. I'll then click on the trash can and eliminate all the operations. This essentially deleted all the machining on this part. What we're going to do now is set up some cutting conditions and face, rough turn, groove, thread this piece of geometry. I'm going to go to top view, and my machining palette probably looks different than the one you have in your shop or office. The reason being is that I have the ProAxis module installed, and it appears right here on the machining palette. The machining tiles are similar to the milling package. They are the contour, roughing, threading, and holes. The tools that I've described are right here in their appropriate tiles. And we'll take a look at the tool definition for a moment. If I double click tool tile number 1, we'll see that turning tool number 1 dialog window appears with a series of tiles that are lined up by category. They are set up as 80 degree, 55 degree, 36 diamonds, round, square, triangular tools, trigon, pentagon, and the Kennametal style 55 degree top-notch roughing tool. We can also define rectangular, groove, cutoff tools. Threading tools are defined as a normal threading tool with the top-notch style, the cresting laydown style, and a 35 degree with a radius for specific threading. The form tool can be defined by drawing geometry at the origin of the part. Hold on a second, guys. I'm running into a problem here. I'm going to pause the presentation for a moment. Nobody can hear me. Not connected to audio. This guy's connected to audio. They're not connecting is what's happening.
Bo tried to connect, he can't hear you either. So most people can't hear you.
Connected to audio.
Do you have a chat capability in there?
This is
Start broadcast.
The broadcast is now starting. All attendees can now hear you.
All right, gentlemen, we had a glitch in the software. I'm hoping you guys can hear me now. All right. For that brief time, I'm going to go back and reiterate what I was saying. I'm sorry. I apologize. We ran into a glitch in the connection with the audio connection here. Hopefully, everyone can hear me now. Going back to the tool dialog, as I was previously explaining, double-click tool tile number 1, and we will see the tools defined in categories. The categories are diamond tools, 80 degree diamond, 55 degree diamond, 35 degree diamond. We've got a round insert, square insert, and a triangular insert. A trigon, pentagon, a 55 degree style, top-notch Kennametal style roughing insert, rectangular, grooving, and cutoff inserts. Threading inserts, standard top-notch Kennametal style insert, cresting, laydown style, and a 35 degree threading insert with a radius. A form tool is defined by drawing geometry at the origin of the part and applying it like a normal tool. When selecting a tool tile, you click on the tile and you come over to the tip radius selection drop-down menu and you specify the tip radius. The inscribed diameter controls the size of the insert. The larger the inscribed diameter, the larger the insert. The thickness is the thickness of the carbide insert. And if I select tool holder, you'll see that I've defined a C432. The C designation is an 80 degree diamond. The 4 represents the inscribed diameter in units of 1/8 of an inch. 4/8 equals 1/2. The number 3 is the thickness of the cutter in 16ths, 3/16. And the 2 is the tip radius in 64ths. 2 64ths equal 1/32. When we select catalog criteria, we're able to see the tool holder. If I select other, I can define an insert of my choosing, but I will not see a tool holder. Going back, unchecking other, and activating the tool holder shows us the tool holder in the proper orientation. The red plus sign represents the touch-off point on the part. The spindle direction is controlled as forward or reverse. The offset number is number 1. The catalog information appears to the right of the viewport, and if I use the scroll bar, I can see a different assortment of holders that will hold the same style insert. I'll select the first one. That is the most practical one to use in this application. Tool material is a coated carbide insert, and the offset number is based on the tile location. If tool ID is checked, the tool call number can be input by the user in this dialog or text edit. This is typically used when you have a pre-tooled turret and your tools are in a known location. You can use that as your first tool in the Gibbs program, but it may reside in station number 10 on your turret. By using tool ID, when you post-process the code, you're going to get T10 offset 10. If this is unchecked, I change this back to 1, it will give me a T0101, tool offset, tool 1, offset number 1. So order of placement along the list. Hold on one second, gentlemen. Let me pause this for a second. What?
The video screen's not changing.
Is it better now? All right, gentlemen, we're running into some technical difficulties here. Hopefully everything is coming up all right. All right, what I think we're going to do, gentlemen, is start this session back up a little bit. We're having these technical difficulties here. What I'm going to do is I'm going to back up the session. Let me pause it for 1 second. All right, gentlemen, I apologize. Hopefully all the bugs are worked out now. Okay, we're going to start once again with the tool list. I will reiterate, sorry for the inconvenience. Tool tile number 1 shows us the tool categories. As I've mentioned previously, and most of you may have not have heard me, some of you may not have seen it. We're starting with tool selection for facing and turning with this particular insert. This is an 80-degree diamond, and inserts are defined in categories. As diamond inserts, 80-degree, 55-degree, 35-degree diamonds. The round, square, triangular inserts, trigon, pentagon, and the Kennametal lay-down style 55-degree roughing insert. We can define rectangular, grooving, cutoff inserts. Threading inserts are defined like the normal top-notch style, the lay-down cresting style, and a 35-degree with a radius. A form tool is defined by drawing geometry at the origin, the point of contact is at 0. So depending on how you draw your geometry, you control the touch-off point by placing that portion of the geometry at 0. The radius information is defined in these dialogues right here. We've got a tip radius of 1/32, inscribed diameter of 1/2, and a thickness of 3/16. This essentially is a CNMG 432. If I select tool holder, I get a picture of the tool holder with the insert in the viewport and the catalog designation on the right of the viewport. As I scroll down, I see different holders that I can use to hold the same insert. I'm going to go back to the first one, select the first insert, or I'm sorry, the first holder, and see that the designation is C432. The C represents the 80-degree diamond. The 432 designation is the tip radius, inscribed diameter, and thickness in units of a 1/8 of an inch, a 1/16 of an inch, and a 1/64 of an inch. The number 4 represents 4/8, which is the inscribed diameter of the insert, 1/2 inch. The number 3 represents 1/16. It is the thickness of the insert. And the number 2 represents 1/64, which is the radius. 2/64 equals 1/32. That's your tip radius. If I have an insert that does not meet catalog criteria, I can define by selecting other and putting in my own values. This is commonly used for grooving inserts or maybe odd size inserts that aren't contained within the catalog selection. If I uncheck other, it reverts to the original selection. I check tool holder and I see my tool holder. The spindle direction is controlled forward or reverse. The offset number is based on the tile location in the tool list. If you have a pre-tooled turret and the first tool that you're using in your program in tool tile number 1 is actually in a different location on the turret, you can turn on tool ID, type in the turret location. For example, let's type in 10 and the offset 10. When we generate the code, it's going to give us a tool 10 offset number 10. If it's in a different position, we can change the tool ID number and the code will output T6 offset 6. If tool ID is not selected, the tool call in the code is based on the position in the tool list. The tool material, coated carbide insert. Tool comments, I can type in CNMG 432, and if I hover my cursor, close this up, hover my cursor over the tool, it'll say CNMG 432. So any tool comments can be typed in here, and if you hover your cursor over the tool tile, you'll actually see the comment appear. The tile here is to access mill tools. In a mill turn application or an MTM application, sometimes it's necessary to select mill tools, and we can select them by clicking on this icon here. Tool number 2 is actually a mill tool. So we've selected the milling tile from here, and we see the selection of mill tools appear on the left, and we get a to lathe tools tile that will return us to the lathe tools. So we've got a CNMG 432 for facing and turning. We've got a a center drill, half-inch drill for the through hole. We've got a boring bar, a finishing insert, and a couple of grooving inserts. And the last operation is a threading operation. We'll revisit these tools as we apply them to the part. The first operation is going to be to remove 100 thousandths from the face of this lathe part. This is done by dragging tool number 1 down to process tile number 1 and the rough turning tile on top of that. The process dialog window appears. We have a series of options. We have 3 choices for applying the machining. On the OD, the front ID, or the front face. We mentioned that this was going to be a facing operation, so we'll select front face. The cut direction is forward instead of back and forth. Start side extension can be typed in as a value to start off of the part. In our demonstration, we're not going to use the start side extension. We're simply going to place the start marker outside the stock. Rough turn type. We specify the radial, in this case, the axial amount. I'm going to type in 50 thousandths in Z. Take this material off in 2 cuts. Corner break 0, and I'm going to go right to finish. Establish my finished face so that I can touch off my other tools right on that finished face. The checkbox for CSS stands for constant surface speed. This is the G96 command that gives us the ability to alter the RPMs as the part is being machined. CSS starts the cut and increases the RPMs as the tool moves closer to center, maintaining the same metal removal rate. CSS is programmed by giving it a cap or a limit, a not to exceed. I'm going to give it a not to exceed 3,500 RPMs. This is typically shown in the code as a G50 command before the G96. Surface feet per minute is the way we program the CSS. I'm going to go with, let's go with 1,200 surface feet per minute. It's aluminum. We've got a decent grade of insert. And I'm going to use a feed rate of 10 thousandths per revolution. It'll give me a nice cut on the face of this part. Use auto clearance should always be checked. This, as I mentioned previously, allows the system to determine the clearance values based on this value here. Each pass will be cleared by that amount. This is found in the document control dialog in the auto clearance dialog. Rough style, material only with a clearance value, or full. We're going to stick with material only, which these 2 dialogues or these 2 options should be used the majority of the time. This automates most of the clearances and machining and keeps the part from being overcut or gouged. Cutter compensation is unchecked. I am not a fan of cutter compensation on lathe. I find it to be more troublesome than it is helpful. The fact that gibbscam generates the code from the center of the radius on the insert eliminates any need for cutter comp, and you can just use your wear offsets to adjust for size. Flood coolant is our selection. That's on. You notice that preferred canned and auto finish are unchecked or grayed out, also unchecked but grayed out. They are not active with auto clearance. The reason being is that the preferred canned generates a can cycle, and can cycles require a fixed set point to generate the moves. With auto clearance, we don't have that fixed set point, so we can't use the can cycles. If you have a need for a can cycle, simply turn off auto clearance, make sure your clearance values will clear the part, and then go to full, and you can use the preferred can and the auto finish. In this case, we'll stick with auto clearance and material only. The cut direction axis will come into play shortly, and I'll explain what those do in the subsequent operation. Go ahead and close the process tile, and the process tile can be closed by clicking on the X here, or a simple Control W, which is equivalent to a close window command, will also close the window. We're going to machine 100 thousandths off the face of this part. I'm going to go to top view. Make sure that I'm flat on the screen. And I'm going to zoom up in this area and select the face as my start feature. The markers appear, and I'll take a moment to explain the markers. The markers appear anytime you select a feature. Anywhere you click, you'll get your machining markers. If you want your markers in the midpoint of a feature, simply click on the feature, hold the control key, click off the part, and the markers will snap to the midpoint of the selected feature. In this case, we're going to start machining on the face. The two circles that appear represent the tool or the insert itself. Cutting on the right or cutting on the left of the selected feature. The arrows determine the cut direction. The white square marker is the start feature selector. The black square marker is the end feature selector, and we'll get some more understanding of this as we progress through the part. The white circle is the start machining marker. I drag that off slightly above the defined stock. You notice that even if I drag it over to the side, it'll snap in line with the selected feature. The fact that the white square is on this feature locks the machining marker to that feature. So we'll just drag it slightly above that. The black circle marker is the end machining marker. We'll grab that and drop it right at XZ0. The dark blue line represents the tool path, or where the tool is going to cut. The arrow determines the cut direction, as I mentioned. If I click on the do it command, we see the tool path appear and an operation appear on the right margin of the screen. Let's take a moment to understand what's going on with what we see in the tool path. Get this out of the way here. The white dotted lines are rapid approach moves. The solid orange are feed moves within the tool path. The dotted orange are rapid moves within the tool path. If we were to see any solid white lines, they would be feed approach moves. This move at the end is where we're doing our auto clearance move in X and Z before we return to home. Previous view shows us that once again. Go to isometric view and turn on the rendering. Now the rendering, I've selected Flash CPR. Flash CPR allows me to run the rendering and move the image, zoom up, do whatever I need to do to the image to view it correctly without regenerating the rendering. If Flash CPR is not selected, we go to normal CPR and turn it on. anytime I move the image, it regenerates the rendering. It's quicker than the Flash CPR, but it does not retain the image. Let's go back to Flash CPR. Turn it back on, and I can see what the cut is like and after it's machined and move it around. If I want to single block, I go to next feature. Just a quick rundown on what we see on the Flash CPR control panel. We see the operation number, a rewind tile, a stop tile, a next feature which is equivalent to a single block, the play button which will do a continuous rendering, and the skip operation tile. In these three tiles here, we have the show stock only, show a transparent tool, or show solid tool. And the speed of the rendering is controlled by this slide on the control panel. Right mouse clicking the top of the control panel gives us a drop-down menu that allows to set up start and stop numbers. I can tell it to start at a given operation, stop before a given operation. I can select to use the op start or the op stop or both. The time selection shows us the time instead of the operation number. As you can see, the difference is the operation number or the time. Transparent stock, transparent fixtures are commonly used when working with solids. For rendering a peg drilling cycle, you can skip the pegs and just watch it go into full depth and retract without wasting time watching all the pecking. Skip unselected ops is a handy feature when you have a large number of operations and you want to skip some of the operations that you don't wish to view. You can skip the unselected ops. We can turn on collision checking. Save to STL saves the rendered image as an STL file that you can re-import into another file or even the same file and use it as part stock. Create facet body will take that same image and create a faceted body from that image. And if we were running simulation, we could reload simulation. Now in the settings for Flash CPR, we can control the speed and the quality of the image in Flash CPR. Steps per update should default to 20. If you want to render slower, you make this number smaller. If you want to render quicker, you make this number larger. The cut part chord height and body chord height default at 1.5 thousandths. This is the quality of the image. If you increase this number, the image gets rougher, more faceted. It will generate quicker, but the quality has suffered. Also, the quality of the tool appearance has suffered. So we'll just go ahead and leave this at 20 steps per update and 1.5 thousandths on the cut part chord height and the body chord height. So just a brief rundown of what's happening with the Flash CPR. If I choose next feature, I can single block through my operation. If I turn on my tool holder right up here in the taskbar, rewind it and single block once again, I'll see the tool holder and the insert perform the operation. All right, I'm going to turn off rendering, go back to top view, and that operation was successful. I'm going to go ahead and keep it. And in order to lock in the tool path or keep the operation, you deselect the operation tile on the right by clicking an empty tile, and this locks in the operation. I will now click off the part to eliminate the markers and the tool path. And the process on the lower left is going to be used to rough turn this part. So I'm going to double click the process because it is using the same tool in the same roughing conditions. But this time I want to rough the OD of the part. Cutting forward, start side extension again 0 because I'm going to control it myself. Rough type, I'm turning with a cut depth of 50 thousandths radially, so it's 100 thousandths on the diameter. Pull off wall allows the cutter to pull off after it's cleared the cut instead of machining all the way up the face. In other words, if I was machining this part, it would cut across here and then feed up the face. Take another pass, feed up the face, another pass, and feed up the face. If I select the pull off wall, it will take a pass, clear, pull off the wall at an angle, reposition, and take another pass. So we'll go ahead and select that, and I'll show you the tool path as it appears. Different options, plunge, pattern shift. Plunge is the rough plunging condition, cycle here. We'll be using that later on. And the pattern shift. Pattern shift is a G73 pattern shift cycle, which will take the finished contour and move it in gradually in Z and radially in X based on these values here. We're doing a simple turning operation in this case. Corner break, 0. I'm roughing, so I'm not concerned with breaking the corners. Finish stock. Now, finish stock is a uniform stock allowance equally placed on the radius and on the faces of the part. XR stock and Z stock split up the stock allowance to the radius and to the faces. If I was to use a uniform stock value of 30 thousandths on finished stock, it would leave 30 thousandths on the radius and 30 thousandths on all faces. When I went to finish this part or run my finishing operation, my tool would have a tendency to bury itself on the face before it continued cutting up the face. This would probably chip the insert or maybe even knock the part off center. Uniform stock is fine when doing straight work without shoulders or radial features with angles. That's fine. But in a situation like we have here, I prefer to use XR stock of 30 thousandths and Z stock of only 5 thousandths. This way, when I perform my finishing operation, I'll only be taking 5 thousandths off the faces in Z. CSS will stay in effect. Look at the picture up here. We're cutting on the OD. We're using auto clearance, material only, and flood coolant is on. All the cut direction axes are checked. Once I've satisfied the inputs, I close the dialog window, and we're going to begin the machining on the chamfer and finish the machining on the OD slightly past the end of the part. All right, I'm going to zoom up right here, select the chamfer as my start feature, and you notice the markers appear with the cutter on the outside of the geometry and the cut direction pointing towards the chuck. My markers are all grouped at that same location. I'm going to move my start marker 50 thousandths off the face of the part. But instead of dragging it and guessing where 50 thousandths is, I'm going to right mouse click it, move start point by 0.05, apply it, and watch that white marker snaps 50 thousandths in front of that selected feature. I'll close this window, unzoom my part. I want to finish the cut on the OD 50 thousandths past the end of the part. I right mouse click the OD, move end feature here. It automates the movement of the end feature markers to that location. Right mouse click the black circle, move endpoint by 0.05, apply it, and it moves 50 thousandths past the end of the part. I can increase that value if I like, 0.125, and it moves 125 thousandths beyond the end of the part. So for the end feature, it takes the end of the feature and uses that as the reference point. And for the start feature, it takes the start of the feature and uses that as the reference point for the movement here. All right. The dark blue outline shows the area that will be cut. I'll say do it, and I'll see my tool path. I'll render it. And turn on my geometry. Control open bracket will superimpose the geometry onto the rendered image. And you notice that we've got a couple of cuts that we're really not too happy with. We've got a cut that's trying to go into here, this groove here. We got a little cut here and a little cut here. If I turn off rendering and look at the tool path, we see that cut trying to go into the groove and over here also. Now, to eliminate any motion into these grooves, I double click the process, and the cut direction axis will inhibit a cut in a given direction. In this case, I don't want the cutter to dive into the grooves, so I'll uncheck the X minus dialog or checkbox, close the window, redo the operation. I'm going to zoom up right here first. See that cut right there? When I redo the operation, I expect to see that cut straight across the groove. Same here and here. Just to show you the difference, I'll undo that cut. There's the extra motions, and there's the resulting cut with the X minus unchecked. Okay, if I render it and show the geometry, we see that we're no longer diving into the grooves. Okay, turn off rendering, and I'm happy with this operation, so I'll deselect the operation to lock in the toolpath, click off the part, eliminates the markers, and at this point, I'll throw away the process. I'm going to start a new operation with a clean slate. And this is always recommended. When you're going to start a new operation that doesn't use the same tool or the same process, always deselect your operation, deselect the part geometry, and throw away the process. This ensures that you don't overwrite any previously created operations. What we're going to do now is a multi-tool operation. We're going to spot or center drill and drill a 1/2 inch hole on this part. So I'm going to group the tool number 2 in process tile number 1 and bring down tool number 3, process tile number 2. Combining these two tools will apply them to the same selection as a unit. We'll take our holes process, drop it on process tile number 1, and the cycle options are feed in, wrap it out. Feed in, wrap it out typically generates a G81 cycle when using CAD cycles. G81 with a dwell would be a G82. So if you want to introduce a dwell, this is the location. Feed in, feed out is the second option. Feed in, feed out lets us feed to depth and then feed out to the clearance plane. This is best suited for reamers, maybe for a reaming operation or a simple straight boring operation where you don't want to leave any tool marks as you exit the work. A tap cycle generates a G84. Rigid tap generates a different code. Now, it's important that you make the right selection because this controls the the G code that's output. A tap will give you a G84, a rigid tap maybe a G84.1. Completely different cycles. PEC with a full out is a G83 cycle. PEC with a chip breaker, a G73 cycle. Both of these cycles activate a couple of dialogues for clearance and the PEC amount. PEC with a full out, the clearance is the amount that the previous cut will wrap it back into before it starts pecking. In other words, it'll take a peck, wrap it out of the part, wrap it to within 50 thousandths of the previous cut, and then take another peck. With a chip breaker, it'll take the peck amount and then retract enough to break the chip and then continue pecking. In this particular case, we're using a center drill. So I'm going to use a feed in, wrap it out with a dwell of 0.25. We're going to dwell for a quarter second at the bottom of the cut. We can also specify a dwell by revolutions as a time increment or by number of revolutions, maybe 5 revs. It's 0.3 of a second. That ensures I get a nice clean surface so that my drill enters straight in. The depth of cut when drilling or when doing holes can be defined in one of 3 ways. This dialog here establishes the start of the cut, right on the face at 0. This dialog controls the depth of cut by diameter. If I want to pre-chamfer a hole, I can specify a diameter and it'll chamfer only to that diameter on the angle. Once it passes the angle, it becomes full size. But I can specify a diameter within the angle of the tool. The other option is the other option is to the tip. I take the depth of cut to the tip of the tool. And the other option is to the shoulder of the tool. So in this particular case, I'm going to take the center drill, a minus 0.275. The other 2 fields update automatically. And this will drill 275 thousandths into the part based on the tip, dwell for 5 revolutions, retract, and go home. Okay. Bring the holes process down on process tile number 2. This particular tool is going to be a PEC with a full out. The clearance 50 thousandths, PEC 0.5. The PEC defaults to the diameter of the tool. 0 dwell. And we're going to take this tool all the way through the part. So I'm going to say minus 4 inches to the shoulder of the tool. This ensures that the hole goes all the way through the part. We're using auto clearance, the speed, 1,000 RPMs with the feed rate of 10 thousandths. We'll close the dialog. Now you notice that the Do It button is already lit up. I don't have to select anything because I have already specified where the start of the cut is at Z0. And the fact that we're in lathe ensures that we're only cutting on center line. So the Do It button is highlighted. I say Do It. The toolpath appears. I get 2 operations on the operation list. If I go to isometric and render it, I can see the cut on the inside. There's a 1/2 inch hole going all the way through the part. Okay, happy with that toolpath. We'll deselect the operations, turn off rendering, and throw away the two processes. We're going to start operation number 5. Operation number 5 is using tool number 4. Tool number 4 is a 3/8 diameter end mill. I'm sorry, not end mill, boring bar. 3/8 diameter boring bar. Tip radius 1/32. Inscribed diameter 1/4 inch. Inscribed diameter controls the size of the insert, hence controlling the size of the holder. If I change my inscribed diameter to 3/8, the boring bar appearance changes in the viewport. It gives me a minimum bore requirement of 770 thousandths, and that's too large for that 1/2 inch hole that we've already drilled in the part. So by controlling the inscribed diameter, I see the correct information here. I've got a minimum bore requirement of 480 thousandths, so that'll work just fine. But look at my tool. Looks a little funny. Go to the viewport and you'll see different styles of boring bars. We'll go with the second style here, which will fit in that hole nicely. Let's go ahead and close this dialog window. And we're going to do this as a roughing operation. Bring down tool number 4, and we're going to bring down the rough machining tile right on top of that process tile. In this particular operation, we're going to do the machining on the front ID. Notice that the graphics changed to represent an arrow up and an arrow down. We're using auto clearance, so those values are determined for us automatically. Forward spindle direction, my cut depth will be 30 thousandths radially. It's a smaller diameter bar, and we don't want to push it with 50 thousandths. I think we can take a couple of 30 thousandths passes. Corner break will be 0. We're going to break the corner. No, I'll tell you what, we'll give it a corner break of 10 thousandths. Finish stock 0, XR stock 0, Z stock 0. We'll go right to finish. And close the dialog. Zoom up on the mouth of the part, and we're going to machine this area right here. I'm going to start the cut right there on the outside, cutting in this direction, and I want my end feature marker right here so that I can break this corner. So I right mouse click and move end feature here. Like so. I say do it. There's my tool path, automatically generated. It clears. I render it and show the geometry. We see that we're cutting right to the line, and we still have material on the OD. Okay, so show the part. We'll rewind, show it from scratch. We've got the facing operation, rough turning, and center drill, and counter bore. All right, satisfied with the results. We deselect the operation, turn off rendering, go to top view, and click off the part. All right, next operation. We throw away the process. And the next operation is done with it 35-degree diamond tool. This is a profiling insert, 1/32 radius, inscribed diameter of 3/8, thickness defaults at 3/16. We show the tool holder, and this is the proper selection for this operation. I could select different holders, of course, but we'll go with the first selection. All right. That's the tool we're using, and we're going to use a contour pass. We're going to take one pass on the contour. On the OD, forward cut direction, entry exit moves will all be 0. Once again, we're going to control the start and end point ourselves. and we will give it a corner break of 10 thousandths. Close the dialog window. Once again, I'm going to select the chamfer as a start feature. Right mouse click my start marker. Move start point by 50 thousandths. The number that appears is the actual location of the marker. So that's what you're seeing there. The end feature, move end feature here, right mouse click on it, and right mouse click the end machining marker. And you see that number there is the location of the marker on the feature itself. As I move it, you can see how it reflects the location. Put a 0.100 there and push it 100,000 past the end of the part. My previous cut was at 125 beyond it, and this one I'm keeping it a 25 thousandths back so it doesn't go into a large piece of material. Close this dialog window, do it, and let's look at the results. Once again, we're getting the tool trying to dive and machine in the grooves. The system pushes it as much as it can. It actually fits down in here. But here and here, it would be a pretty heavy cut and probably chip the insert or move the part. So what we're going to do to eliminate that condition, double click the process, uncheck the X minus dialog, and watch the toolpath when I redo it. It should straighten up right across the grooves and giving us a corner break with an automatic clearance there. Render it, and we'll see the result. Zoom up here, we can see the little 10 thousandths corner breaks, and pretty good result there. All right, satisfied with that result, I'll deselect the operation, throw the process away, and click off the part. This gives me the clean slate to start the part. And what I'm going to do is do the thread relief and the O-ring groove, and then this larger angled groove, and thread the part. So tool number 6 is brought down to process tile number 1, and we're going to put a contouring operation onto it. We're cutting on the OD using auto clearance, forward cut direction. No drag is the option that I want to use. No drag is a very good feature for grooving. It takes a cut on one side of the groove, retracts, moves to the other side of the groove, takes another cut, and then cuts across the bottom instead of trying to cut down one side and push all the material to the other side. So we're going to select no drag. This turns off our entry and exit moves. You notice that I haven't changed the CSS values at all because CSS controls the RPMs determined by the diameter of the cut. And we've already given it the cutting conditions, not to exceed 3,500 RPMs, and to use 1,200 surface feet per minute with a feed rate of 10 thousandths per revolution. Now, all the other values remain the same. Close the dialog window, and I'm going to zoom up to this thread relief. Select this side, arrow down, and right mouse click the marker and type in a 0.05 value. Moves 50 thousandths above the part. Right mouse click the angle, move in feature here, take this and move that by 50 thousandths. I'm just using 50 thousandths as an arbitrary clearance number. Cut direction down, say do it, look at the toolpath. Now let's see if we can't view this toolpath slowly here. Let's go We're going to hit operation number 7, and we'll see. I'm single blocking through the operations now, and I'll get to 6, and here's number 7. If you notice with the no drag option, the cutter comes in, positions, cuts down, retracts, repositions, cuts down the angle. Now it cuts across the bottom and leaves the work in that manner, not pushing all the extra material down here. This comes down and then down this way and across. Show the geometry, and there it is. Turn off rendering, deselect the operation. I'm going to do the same thing on this O-ring groove, but I'm going to break these corners. I think I've got a 10,000th corner break here. I want to break these corners so that they're not sharp. So in order to cut this groove with the no drag option, I'm going to start the cut on this side, finish it on this side, and this will give me the corner break that I specified. When I hit the do it command, render it, and we'll single block to that cut. There it is. Corner break, exit, other side, corner break, cut, feed across the bottom, and leave the work, show the geometry, and we can see that we've cut it right to the line. All right, I'm satisfied with that result. We will turn off cut part render, deselect the operation, click off the part, and unzoom. I'm going to use this same tool, and I'm going to rough in this operation right here, or this groove right here. So bring down the tool, it's already there. Bring down the roughing tile, and I'm going to plunge. Plunge angle defaults to -90 based on the tool orientation. The cut width can be either constant or details. Constant is best suited for square shouldered grooves. It'll give you a constant step over based on this value here. Details will give you a step over, but alter the step over based on the shape that you're cutting. So it's going to be a 50,000th max step over. So when I have angles, I want to create like a stair step effect. I'll use details. Center cutouts, when selected, takes a cut in the center of the groove and works its way from there towards the Z negative direction or the Z positive direction. So it relieves the material in the center of the groove. The plunge type can be a peck with a full retract or a peck with a chip break cycle. I'm going to select plunge. We'll just take it straight into depth. The first plunge, the feed is reduced by 50%. The subsequent passes are at 100% feed. We'll go ahead and close the plunge dialog, and we'll leave this active. Let's take a look at this. Let's see what happens here. Zoom up here, select this side of the groove, take the start machining marker out here, cut direction downwards, right mouse click the opposite side of the groove, move end feature here, and drag it slightly upwards. Do it. And what did I do wrong here? We have a 90-degree, oh, I'm sorry. I know exactly what I did. OD. I need to be on the OD. See, the system was smart enough to tell me that my approach was incorrect, and it was right. I messed up. Redo it, and there's my plunge cycle. Bring it in, slow it down, and we'll see it do the machining. All right, turn off rendering. We're satisfied with that result. We'll take and throw away the process, and we'll finish this groove with the larger insert as a contour cut. This cut will be a no drag, corner break of 10 thousandths. Everything remains the same. We'll start on this side, cut in this direction, and end right over here. We do it. And in this case, I'm going to turn off auto clearance and control where I start. Just to keep it a little bit tighter. All right, there's our rapid moves, there's our feed moves. Turn on rendering. And we should see machining performed on the entire part. I noticed that this is gray. The yellow operation shows us where material was removed. I just noticed that I did not leave, in this previous operation, I did not leave any stock for cleanup. So I'm going to go with XR stock of 15 thousandths and Z stock of 5 thousandths and simply redo the operation. Now, when I re-render it, I should see that entire groove in yellow. There it is. So now I'm showing material removal. I had failed to leave any material on the previous operation, so it didn't show me yellow on the bottom. I redid the operation by leaving material, and now I see the entire cut. All right, turn off rendering, deselect the operation, and throw away the process. The last operation is going to be a threading operation. The threading tool is defined as a thread LT, the cresting style. The style is UN as opposed to a UNJ and ISO and NPT, ACME. You've got a series of options here. Go with the standard UN class. Threads per inch based on our blueprint was 12 threads per inch, and the tool is defined in the viewport. Close the window, bring down the tool and the threading tile. The threading tile activates the thread dialog window, and it gives us all the threading options. The cut options, Z minus, Z positive on the OD or the ID. Z minus generates a right-hand thread. Z plus will generate a left-hand thread. For Z plus, you start at the back of the thread, go in the positive direction, and generate a left-hand thread. The infeed, there's two options. There's balanced and thread angle. The difference being that balanced, the insert enters the work at 90 degrees or perpendicular to the cut. Thread angle enters at 29.5 degrees, which is like using a compound slide on a conventional lathe. If any of you guys have ever done any single point threading and use a conventional lathe, you know that the compound slide is set at 29.5 degrees, and that's how you approach the work. The alternate checkbox is used to alternate multiple passes. In other words, it'll take the first pass with the leading edge of the insert. The second pass will alternate to the trailing edge of the insert and alternate back and forth from leading to trailing edge, giving you a much cleaner thread and extended tool life. If anyone's ever cut a 3/16 stainless, try to thread it, you know that the back side of the threads get pretty galled or pretty rough looking. By using the alternate method, you'll get a much better result on the thread. The style of the thread defaults from our tool definition. The nominal X diameter. We're going to machine a 1-inch 12 thread. I'm going to give my nominal X diameter as 0.999. This will take me 1/1000th under the high limit of the thread. Threads per inch defaulted to 12. Taper or slope, 0. If we wanted to generate national pipe threads or NPT threads, we would specify a slope, or we would use the processes contained on the CD for NPT threads. Number of starts, it's a single start thread. If we had multiple start threads, the way to do this is you divide the threads per inch by the number of starts and fill in the dialogues accordingly. Major X diameter, 999 based on this value. The minor and the thread height default based on this information. Now the depth of cut. The depth of cut can be performed as a one finish pass, which is great for chasing a thread. It can be done as a constant cut by specifying a radial cut that steps down constantly up until the last cut, where you specify the amount of the last cut. Or you can use constant load, which is preferable, I believe, because it keeps the load on the spindle the same throughout the threading operation. It diminishes the depth of cut the deeper the tool is engaged in the work. Take my first pass at 15/1000ths. All the following passes will diminish in depth up until the last cut. Last cut, I'm going to uncheck it. I'll let the system worry about it, and I'll generate one spring pass to eliminate any deflection that may occur from the threading operation. The speed, I'll just click on the speed RPM tile, and it gives me the recommended value. Flood coolant is on. And let's take a look at this graphic right here. Run out and run in. Control the exit and the entry of the thread. Fanuc style, chamfer on, chamfer off, M23, M24 represents what these values do. In a situation where I have a thread relief, I'll make my run out 0. This will exit the work at 90 degrees or perpendicular. Notice that the run out values are radial. If I wanted a 45-degree angle at the end of my thread height is 51/1000ths. I would use a value of 60/1000ths here and 60/1000ths here, and I would exit the work at 45 degrees. This is a nice feature when doing a shaft, and you want to get a nice clean thread at the end. Chamfer it with a run out. In this case, we're going into the shoulder, so we're going 0 run out. This dialog here, if you follow this line here, it represents the end of the thread, minus 0.9. I'm going to go in to that thread relief. The start of the thread, 0 the face. The run-in, 0.16667 equals the pitch of the thread times 2. This is a default value that it starts machining 2 threads in front of the face to ensure that you have a perfect thread in the cut and it gauges correctly. I'll go ahead and go with the default value. We'll close the dialog window, and the do it command is already active because we've already specified where the thread is with these values here. It starts at 0, finishes at minus 0.9. We've got the diameter and the pitch. We say do it. The thread operation appears. and we render it. We see the threading. All right. Go back to full size. Stop this operation and render it. All right, folks, so there is the hub or the part that we started kind of haphazardly this morning. I sincerely apologize for the technical difficulties. It looks like we've got them ironed out. I'm going to attempt to answer any questions. If you have any questions, please raise your hand and I will try to connect with you and answer your questions. Thank you for attending, and we will be holding more of these sessions in the future. We will get better at it. We will get to the point where they'll all be recorded and we'll be able to distribute them. But the goal is to have at least one session per month and get a pretty good library of all the functions so that it'll help our customers utilize the software better. Thank you, guys. If you have a question, please raise your hand and I'll try to answer it.